Okay. Here today, and I have INL. Maybe some of you heard of it. And by some chance, me and Marina, we just got interested in this project. After a conference, we decided that we are going to do it in 2 days, and we delivered some first version of the algorithm, and then fine-tuned it for like 3 more months or something. So this is going to be interesting, I hope. And I'm going to start with the framework first. And so by the way, the topic said that this is a complex paraphrase detection. In fact, it's a more broad topic of plagiarism detection. I will tell you in a minute how they relate. So plagiarism detection is a competition that is organized annually by an organization called PEN. Okay, I see how it works. Now, it was organized mainly in English before 2017, where there was a first dataset for Russian language delivered by the people who presented in Dialogue in 2017. This is Smirnov and Sochenkov. So this was the first competition. They had some kind of shared task where you ask participants to submit your algorithms and then evaluate on the common framework. So broadly speaking, plagiarism detection is an umbrella term which combines several tasks. And one of the main tasks in this domain is external plagiarism detection. External plagiarism detection is something that is mostly well accepted by this term, which means that you have some kind of text, maybe an essay, maybe your thesis, and the people who want to be sure that you didn't take some parts from the text, they check it from other external sources. This task is split in 2 subtasks, which is source retrieval, and basically it means we need to find documents which look the most similar, or they have some parts that look the most similar to some parts in your document. And then we have more fine-tuned, fine-grained problem of text alignment. And text alignment is exactly what we are going to solve. And it relates to paraphrase detection in a sense that in paraphrase detection you have some kind of small texts or even sentences, and these sentences need to be checked whether they mean the same thing or not. Well, text alignment is actually the same thing. So we have a Russian data set from that competition, and I mean, compared to some of the English data sets, it's actually a very good one because it allows to different types of plagiarism, which are copy-paste. This is a direct copying and pasting literally from some source to another. It allows to check paraphrase, the thing that I talked about earlier. This is a slight modification which is done automatically. And we also have manual plagiarism. They are roughly of the same size in terms of data sets. So 1/3 of all passages in this data set correspond to the particular type. And overall, we have almost 10,000 pairs of documents to check. So we have source document and plagiarism document. And some of them contain parts that derive from each other. Yeah, there's been a lot of research on plagiarism internationally, and a lot of methods that usually, in some sense, can deliver the similarity score of documents or text have been applied. For example, topic modeling, word embedding, supervised, unsupervised. Even genetic algorithms have been used lately. And unfortunately, since Russian dataset has been introduced only a year ago, not that much methods were used to tackle this problem. So the first and the only one actually was syntactic and semantic and syntactic parsing for computing text similarity, which was also proposed in 2017. And here in our approach, we aren't going to do any fancy deep learning, honestly. We're just going to do some pretty straightforward approach, which will be interesting not because of the modeling, but more of a framework approach that allows to do some smart pre-processing and post-processing steps that are, I guess, equally important as classification in this problem, as well as to introduce some techniques that will allow to reduce the empirical time complexity of this problem. So essentially, we could train this model very, very fast, and this is also one of the main benefits. And yeah, before we jump into that, let's quickly just go through the metrics in this competition, because this is going to be important in the second part. So we use some kind of intuitive notion of precision and recall, which are usually applied to classification tasks, but they are done sentence-wise. So you have detection in your plagiarism detection system, and you have a golden sort of pair of texts. And these are denoted by S, which is the true case, and by R, which is a detection of your system. And you kind of measure the intersection of these two things. They come from two sources, which is plagiarism and source document, so from two documents. And these like square intersection sign means that it's not just intersection of text, but rather from two different ones. And we also have a notion of granularity, which helps us to measure how essentially small our prediction. So we shouldn't penalize for very small predictions. So if, for example, you say that one character from this text is similar to one character of that text, it's not really useful. We want to see how, in a big way, these texts relate to each other, not like in very, very granular way. And the PlaGDet score kind of combines these two ones. It takes F1 score from precision and recall and divides by logarithm of granularity. So now I'll talk about our method. But first, I have a question for you guys. How many of you are familiar with methods for tokenization, lemmatization, stemming, stuff like that? Okay. Almost everyone. Nice. Then we can just split it, skip it. But really, so these things, okay, we shouldn't talk about them much, but I think that they should be addressed in your articles and maybe in presentations as well, because this kind of helps you to deliver reproducible research. And if someone wants to implement your system, then he should look into the paper and find all the details that are needed. So essentially, we do like simple tokenization, lemmatization of Russian language. We also use part of speech to do better lemmatization. And so at the end, we have a list of sentences which are represented as lists or sequences of lemmas with part of speech text. Now, so we have pairs of text originally, and these pairs of text are comprised of sentences, which I discussed earlier. And basically, we want to match one sentence from one text to another sentence in another text. And we can do this matching in different ways. So we have, for example, in one true case of plagiarism, we have like a short passage of 5 sentences on the left and a short passage of, I don't know, 7 sentences on the other part. So we have 5 and 7. And essentially what we can do is we can say that, OK, each sentence from the left is similar to each sentence on the right. And this is going to be pairwise matching. It will produce 5 times 7 different results, different matchings. But this is not always correct, because sometimes texts go in parallel. So if especially if there's slight modification of texts, we can say that, OK, the first one corresponds to the first one on the left to the first one on the right, and go on like that. And this is going to be parallel matching. So essentially, this is a way to construct training set of our future classification task. And we will try both of the methods, and then we will show that some of them are useful in one context, some of them in another. OK, and classifier, really, it's no black magic, no rocket science. It's just logistic regression, guys, and maybe some of the well-known competitor. Maybe one unusual thing that we tried was Bayesian classifier. So Bayesian classifier is, not naive Bayesian, but just true Bayesian classifier is an optimal model for classification. And the only thing that it needs to be optimal is to have sort of an optimal distribution of a true class. And we tried to derive this distribution by non-parametric kernel density estimation. So this is this was interesting to try to kind of see what is the optimal performance in this task. Well, sort of optimal, because we don't do it exactly. So, and we also train the bias parameter of the classifier. So we can just shift it towards more heavier weights or towards lighter weights. And yeah, another interesting thing is that what is the feature space of this classifier? So we have a pairs of text, and we need ways to compare them. We can come up with very simple ways like this simple token similarity, which are essentially the measure how much left text is included into the right text in terms of actual words and vice versa. So it's left inclusion and right inclusion. And we also tried something very complex, like, we started from pre-trained embeddings, moving on to unsupervised fast text and supervised star space. It was supervised in the sense that it was trained to predict the label, actually. So it was able to predict whether sentences are similar or not. By the way, how many of you guys know about Rus vectores? OK, you should, because this is actually a great source of Russian language embeddings. So it's not like a single method, which I erroneously put here. It's like a data set or database of different pre-trained embeddings. There's multitude of embeddings there. You should go check it out for your projects concerning Russian language. And we did some simple weighting of these embeddings and simple calculation of similarity using dot product. And another thing which is mentioned on the title is that we do negative sampling. So negative sampling is essential in this task because we have pairs of texts. We have pairs of documents, and out of these documents we construct pairs of sentences. So most of the times, one sentence and another are dissimilar. They don't correspond to each other. They mean different things. And in very rare cases, in around 0.1% actually, these pair of sentences are indeed plagiarisms of one another. So we need to account for that. We need our data sets to be less imbalanced, because the imbalance provides us with heavier compute. So we need to train our classifier on hundreds of millions of examples. And also, it kind of slows down the feature generation process. So we need a way to do efficient generation and training of this classifier. And for that, we need negative sampling. One last part of the algorithm is granularity reduction. So this is a technical procedure that allows us, well, guess what? Reduce granularity. It's one component of the measure that, as I told you earlier, is crucial in plagiarism detection, because it allows you to create sort of higher level predictions out of very, very granular ones. I will not touch upon much. And so this is an overall scheme of the algorithm. Highlighted are the main contributions of our framework. They are sentence matching, which is, again, the way how you deal with constructing a data set. Do you do all pairs versus all pairs, or you just go in a filter way? So you go from one to another and see that these things are, so one sentence matches with one sentence, second with second, and you go on like that. Another thing we tried here is negative sampling, as I mentioned, and try to use embedding measures for computing similarity of texts. And this granularity reduction, which actually helped to reduce the final measure a lot by the cost of precision, by some small cost of precision. And here, I think I'll just skip it and concentrate on main ideas. So we had 5 features overall, and we tried to reduce them to just 2. We were interested if that would reduce the performance at all. And it turned out that it did not for several models. In fact, it allowed us to build these beautiful pictures of plagiarism. So these are plagiarism cases for you guys. And so on one axis, you have similarity in terms of tokens. On another, you have similarity in terms of embeddings. These are 2 orthogonal things that kind of measure different aspects of similarity, right? Because embeddings, they encode quite a lot of knowledge, but sometimes they don't account for exact matches, which are essential in copy-paste types of plagiarism. And these are just different types of sampling. So this is the most honest picture, because this is a whole training set. This is literally hundreds of millions of points here. And yeah, you see that they are intermixed. So blue ones are plagiarism cases, red ones are non-plagiarism. And they are intermixed somehow, but clearly, as you see from the left topmost picture, so most of the plagiarism cases are concentrated around these points, around the origin point of the plot. And most of the non-plagiarism are somewhere farther to the right. So you can see the blue line on each plot corresponds to the classification boundaries. So you can pretty confidently do it with even linear classifier in these cases. Yeah, here we also tune some hyperparameters. Okay, and these are the final ones. For each data set, we did some fine-tuning. They turned out to be quite similar, except margin. Margin for classification is needed to be fine-tuned a lot because, well, I'll show you. In the first picture, we used random 1 sampling, which means that for each positive case, we randomly sampled 1 negative case. And in that case, we really needed to fine-tune the margin on the left, on the topmost left plot, because you see, this is a very steep graph, and it's very hard to find optimal value. So we needed to do this fine-tuning. Whereas if you do no sampling, then you can just pretty much pick the 0.5 or 0.8, and you don't have this loss of performance at all. So here I'll just show the results quickly. The interesting thing that I mentioned just today is that compared to the previous method, well, the previous one was Zubarev 17.2, I guess. Yeah, we turned out to be better in terms of final measure, but if you look at it closely, then you would see that precision and recall are somewhat similar, but we did a good job at reducing granularity, which is, you wouldn't think that as an important factor, but it turned out to be. And our simple procedure was able to reduce it almost to the level of 1, which is the optimal value for this measure. And on other types of plagiarism, we do well as well because of the fine-tuning. And yeah, so kind of the final take of this work is, so we tried different measures of similarity for this task instead of just syntactic or semantic similarity. We tried to do some high-level similarity prediction with supervised and unsupervised embeddings, which are great tools, and I encourage you all to try different ones. For example, Rus Vectoris is a good thing. And another thing that we tried to training our classifier, focusing on each type of plagiarism with this fine-tuning approach. And For this thing, it was especially good that our model had just 4 hyperparameters, as I showed you earlier, and 3 out of them turned out to be identical. So it's very good if you do fine-tuning to have like a small set of hyperparameters that you don't waste a lot of time. I'm sure if you have GPUs and a lot of like computational power, you can do it every time, but we just did everything on a single computer, so it made sense. So I guess that's it. Yeah, and obviously state-of-the-art results, I hope, to the day. Yeah, and you can find it available online. We released it on GitHub. Yeah, so that's it for the first part. If you have any questions. Okay. Yeah. Mm-hmm. Yeah. So it's essentially how you set on the higher level. So we have, let's look at it from the perspective of prediction. Okay. So at the prediction time, we have a pair of 2 documents, which the first one is source document, which most likely the plagiarism was derived from. And second one is our plagiarism document, an essay, a thesis, or something like that. And so our task is, given these 2 documents, we need to find all matching short text or passages from the left one and from the right one. So for example, you see that the beginning of the first document matches perfectly with some middle part of the second document. And you need to find the starting and ending position of these matchings. So you need to find essentially 4 numbers, like the beginning and ending on the left document and beginning and ending on the right document of exactly these texts, which are derived. Yeah. Essentially, we have like almost 10,000 pairs of documents, which I described, and around these 10,000, we have almost 80,000 pairs of passages. So in each document, roughly 8 pairs of passages. I will tell about it later when we touch the second topic. Sorry, can you go? So there were human workers. I think there were Yandex Taloka workers, or maybe some graduate students who read who read original articles, for example, from Wikipedia, and their task was to construct a similar document where some of the parts will be rewritten, like a rewriting thing. Yeah, it is. Paraphrasing and manual paraphrasing differ in a sense that paraphrasing is a controlled synthetical procedure. So you just modify like 20–30% of the words with their synonyms, whereas manual is completely uncontrolled by machines. It's just done by humans. Okay, thanks. I will go to the second part. Oh. So this is actually another work published in another conference. And this is a little bit more spontaneous because while we were working on the previous algorithm, we also touched upon like similar competition and similar domains. For example, we tried to adapt our algorithm for English speaking, for English paraphrase, which I told you earlier is a little bit more advanced and developed field. And surprisingly, we got very, very good state-of-the-art results out of the box. We thought that our algorithm is great. It gave us a lot of motivation to proceed and to write a second article to a very esteemed conference called ACL. It's Association of Computational Linguistics. And so basically, 2 days before deadline, we were prepared to show how our algorithm is great. It beats everyone with their complicated deep learning and so on. And then just 2 days before the submission deadline, something felt completely wrong. Because, you know, if your second competitor has something like 0.85 and you have like easily, without any fine-tuning, 0.95, then it rings a bell. And so we decided to like kind of spend some time to investigate what's going on. And well, long story short, in the next 48 hours, they were the most intense days when first we figured out what's wrong, and second we wrote like a short article about it. So yeah, the main points about that, of course, plagiarism is important. Everyone who wrote his thesis in Russia knows that. And it's also hard to detect. Well, data sets for plagiarism detection, not the ones that we discussed in Russian plagiarism, but more of English ones, are sometimes heavily imbalanced in the sense that the hardest plagiarism there is to detect is a summarization plagiarism. So it's the type of plagiarism where you not only rewrite the original text, but you also make it significantly shorter. So you have like combination of 10 essays, and you just copy-paste, like, not copy-paste, but summarize each essay into like 1, 2, 3 sentences each. And essentially you have no original ideas in your final essay, but it's very, very hard to detect. And so what we showed in this work is that the main plagiarism detection framework, evaluation framework, is PlagDet, and it fails to distinguish good systems from bad ones under certain conditions, under conditions of this summarization data set. And we propose normalized version of plagiarism detection framework, which kind of solves, at least partially, this problem. So to answer your question, text alignment problem is the following. We have a plagiarism case, a true case, on the top, which is, we have 2 documents, plagiarism and source ones, and we know their position in the document. What our system does, it tries to provide one or many detections for this true case, and so if we do like union of all these detections that somehow detect the true case, we just need to compute the intersection between true case and the detection case. And by intersection, I mean intersection on the left and intersection on the right independently. So that's all stated on the slide more formally. One main thing that we did is so originally in this measure, intersection of 2 documents was calculated just as a sum. So you do intersection on the left part, then you do intersection on the right part. And then you just sum these 2 values together. What we did is that we proposed an automatic way to normalize these intersections with respect to several properties of the data set. You can see already that these texts are imbalanced in the sense that plagiarism part is shorter than source part. Okay, and this is indeed the case. So if you take the most common summarization, plagiarism data set for summarization type of plagiarism, which is PAN 2013, you see that on the training set and as well as on the test set, you have a plagiarism part which is 10 times shorter as the source part. So they do indeed generate summarizations, but this is actually bad news for our measure because it's not adapted to this case. It cannot distinguish in some cases it cannot distinguish good ones from bad ones if we know these properties beforehand. So this is also a recap of what is PlagDet. Again, we have precision, recall, granularity. And the question is, why does it work poorly? How can I prove it to you? Well, I can prove it by example, and also mathematically. So I'll start with the second. So suppose you have a document D, and you have some short passages within that document. I'll call them S and R for case and detection. So just like here, you have a document D, and you have, for example, on the left document, plagiarism, you have source case, and you have a detection. Now, we can see that, especially if these sources and detections are pretty long, then in some cases, it's because they are all within one document, it's impossible to for them to have intersection less than 0, for example. So if you have very long document, suppose like 1,000 symbols, and we have a case of, I don't know, 999, almost close to 1,000 symbols, then if you have long enough detection, if you have like very long detection, essentially it would be impossible for these two case and detection not to intersect. And this is our lower bound of intersection, which is denoted by A later. We computed exactly. This is a tight bound, yeah. And they also have an upper bound of intersection. Well, this is easy. This is just a property of intersection. It's always less than minimum of the length of original sets. So this is just well-known fact. And we show that actually in one case, in one extreme but actually always true case of summarization data sets. So this detection part on this picture, not only it's larger than the source part, not only it's larger than the plagiarism part, but it's also consists of the whole document. So the whole source document is its own detection, is its own source. Like, it's hard to reason about this in terms of these terms, but the idea is that unlike in previous framework, where we had short sources, short plagiarism cases, we were balanced in the sense of length, here we have just one huge source case, which is equal to source document. And this is a problem, because it means that our intersection is bounded only by our own desire to be like adversary. So it's bound by the length of R, and our R are our detections. So we can increase them almost to any degree, and we can come up with arbitrarily high plagiate score, which is of course not what we as designers want. And so we start to reconstruct. This is a bit more formal, but I'll just highlight the main ideas. So we start to reconstruct this measure by very simple definitions of intersections. So as I said to you earlier, we have just like a direct sum of intersections within two texts. On the inner sum, big sigma, we have like numerator-denominator, and we have two direct sums of these intersections. What we do is that instead we provide normalization of these inner terms by weighting them with constants b and a that were calculated exactly from this lemma. And we do these calculations for each true plagiarism case. So, for example, if you know that, okay, maybe there is some case where source case is not as long as source document, then these constants will adjust. And in fact, in Russian plagiarism detection, this measure doesn't make any sense, because all of the A's and B's will be, so they will be 0 and 1 respectively, and this whole weighting function, normalization function, will be will be identity function. So it proves the utility of this normalization, because on heavily imbalanced data sets, it does its job to kind of provide normalization of these terms in the sum. But in usual data sets for usual plagiarism detection, without this imbalance, it just outputs identical results as plagiat. And so, yeah, we just, so this was a modification of recall. We just say we have new normalized recall. Then we note, oh, there is no. Then we do similar thing for precision. And normalized plagiat is just, well, normalized precision and normalized recall averaged. So here we did some case study. In our paper, we took, I think, three state-of-the-art algorithms that are especially good on these data sets. And we measured, we took their plagiats and we measured their normalized plagiats on the same data sets. So essentially, you can see that on the first test set, the winner by plagiat and by norm plagiat measure is a good state-of-the-art method by Sanchez-Perez. And our adversarial model, which explores these properties of imbalance, comes very, very close on the first one, second. And on the second test, on test 2, it comes first in terms of plagiat. And this is actually, we can understand this if you look at the distribution of lengths in test 1 and test 2. We see that test 2 is even more imbalanced than test 1. So depending on the ratio of imbalanceness, we can get arbitrarily high plagiat. So yeah, and if we introduce normalized plagiat measure, then we see that our adversarial models, these are two models, I will not talk into detail, but you can ask me about them. They suffer greatly. You see that they become, they have lowest possible scores on each test set, and good models actually have a slightly higher norm plagiat, which is a little bit of surprise, but you know, at least we know that they didn't cheat, unlike us. So to sum up, we learned that the standard evaluation frameworks that are widely accepted sometimes need to be challenged, and sometimes we need to test them to see if they indeed let us see what we want to see, which is a measure of goodness and measure of a way to measure our incremental changes in the algorithms. So if the measure cannot provide this sort of fair way to see if our changes are useful or useless, then this measure is useless because it doesn't give us the right direction to go. And more precisely, we showed that normalization of inner terms helped to prevent this data set imbalance abuse on text alignment tasks. And again, our implementation is available freely. You can use it. And thank you very much. I think not, but I will never know until we have a citation, I guess. But one person has contacted me. He told me that he's interested. He's from Iran, and Iranians are another people who compete in this PAN competition a lot. So I mean, they have a lot of English data sets as well as a lot of Persian data sets currently, and one Russian. Okay. Pleasure to be here. Okay.